Hello, students and learners. I hope you are all doing well. Welcome to the Math 23 lecture entitled Absolute Extrema and Lagrange Multipliers. This lecture is divided into two parts. In this first video, we will talk about the absolute extrema of functions of more than one variable. In the previous videos, you have learned how to compute for the relative or local minimum and the local maximum of a function of more than one variable. This time, we will learn what an absolute maximum and an absolute minimum of a function of more than one variable is and how to compute them. So let us begin by defining the absolute extrema. So we let f be a function of two variables, say x and y, whose domain D is a subset of R2, or the two-dimensional plane, and let a point x naught y naught be in the domain D. The absolute maximum of the function f is defined to be the number f of x naught y naught such that f of x naught y naught is greater than or equal to f of xy for all xy in the domain D. In other words, the absolute maximum of f is the highest value of f over all points in the domain D. Likewise, we define the absolute minimum of f to be the number f of x naught y naught such that f of x naught y naught is less than or equal to f of xy for all xy in D. Again, the absolute minimum is the minimum or the lowest value that f takes over all points in the domain D. We say that f has an absolute extremum at the point x naught y naught if it has either an absolute maximum or an absolute minimum at that point. One very important thing to note about the absolute extrema is that it is defined only for all points in a particular domain or region. Let us look at this particular surface. Clearly, at this point, the function f, whose graph is shown here, attains a local minimum. And looking at all the other points in this region, we say that this point also is the absolute minimum of the function. However, this function attains several local maxima or several relative maxima at different points. For example, this function attains a local maximum at this point and at this point and at this point. However, these 2 points cannot be considered as absolute maximum because the function attains its highest value at this point. Here we see that the function attains a local minimum and an absolute maximum at this point, but this point is a local maximum but not an absolute maximum. However, this point is an absolute maximum. The important question that we want to answer in this lecture is, given a function defined over a particular region, how do we find the absolute minimum and the absolute maximum? But before we answer that question, we will need several important definitions. Let D be a region in the two-dimensional plane. Any point x naught y naught is said to be a boundary point of this region D if every disk centered at this point contains points in D and points not in D. For example, this point lies on the boundary of the region D and is called the boundary point of D because if you draw a circle around centered at this point, you include points that are in the region D and points that are not in the region D. A region is said to be closed if it contains all its boundary points. For example, this region contains all the points in its boundary, so it's called a closed region. However, in this region, the boundary points are denoted by dashes, which means that they are not included in the region. Hence, this region is called an open region. A region D is said to be bounded if it is a subregion of a closed disk. For example, this triangular region is bounded because you can draw a closed disk that completely contains this given region. Let us recall the extreme value theorem for functions of one variable from Math 21. It says that if the function f is continuous on a closed interval ab, then the absolute maximum and the absolute minimum of the function f on the closed interval ab always exist. Now we have an analog of this theorem for functions of more than one variable. This is the extreme value theorem for functions of more than one variable, which we will state here for functions of two variables. Let f be a function of the variables x and y. If f is continuous on a closed and bounded region D, then f has an absolute maximum and an absolute minimum on the region D. This guarantees us that if f is defined on a closed and bounded region D, we can always find its absolute extrema. We have seen previously that the absolute extrema sometimes occur at the points where relative extrema are attained. But is it always the case? Let us look at the graph of the function f of xy equals 3x e to the y minus x cubed minus e to the 3y. Here we see that this function attains a local maximum at this point, and that is the only local maximum. However, it cannot be considered an absolute maximum since there are points in this area in which the value of the function is higher than at this point. Hence, we say that the absolute maximum is attained along this boundary, in the same way that the absolute minimum is attained at the points in this boundary. This tells us that the absolute extrema of a function can be attained either at the same points as the local extrema or the relative extrema or at the boundary. In other words, the candidate points for the absolute extrema are the critical points inside the region D and in the boundary. This gives us the following steps in finding the absolute extrema of a function of more than one variable over a closed and bounded region D. First, we find all critical points inside D. Then we consider the curves that form the boundary of the region D. We solve for the critical numbers of f at each of these boundary curves. Finally, we evaluate f at all the points obtained in the first two steps and at the intersection of the boundary curves of D. The largest among these values will be the absolute maximum value of f, and the least of these values is the absolute minimum value of f. To better understand these steps, let us look at a particular example. Suppose we want to find the absolute extrema of the function f of xy equals x squared plus 3y squared minus 4x minus 6y on the triangular region with vertices at the points 0, 0, 4, 0, and 4, 4. First, notice that this triangular region D is closed and bounded, and f is continuous over this triangular region D. Therefore, by the extreme value theorem, we are assured that f will attain both an absolute maximum and an absolute minimum value inside the region D. To find the absolute extrema of f over the region D, we follow the steps we have enumerated earlier. The first step is to find the critical points of f inside D. To do that, we solve for the partial derivatives of f with respect to x and with respect to y and equate both of them to 0. For the given function f, the partial derivative with respect to x is 2x minus 4, and if that is equal to 0, then x is equal to 2. On the other hand, the partial derivative of f with respect to y is 6y minus 6, and if that is equal to 0, then y should be equal to 1. This gives us the critical point 2, 1, and it is easy to check that the point 2, 1 is inside the region D. Hence, we have the critical point 2, 1, which is the only critical point inside the region D. Next, we find points on the boundary of the region D where the extrema may occur. Notice that the triangular region D is composed of three line segments which form the sides of the triangle. Therefore, we look for the critical points at each of these line segments. First, let us consider this line segment, which is a portion of the x-axis y equals 0, where x is from 0 to 4. We will restrict f over this line segment and find the critical point of the resulting function. In other words, since y equals 0, we let y be equal to 0 on this given function, which gives us a function of the variable x only, which is equal to x squared minus 4x. We find the critical points of this function of one variable by taking its derivative and equating it to 0. Thus, 2x minus 4 equals 0 gives us x equals 2. This means that the given function f of xy may have an extremum at the point 2, 0, which lies on this line segment. Next, we consider this line segment, which is a portion of the line x equals 4, where y is from 0 to 4. Just like what we did earlier, we restrict the function f over this line segment by taking x equals 4, and the resulting function is a function of only the variable y. We solve for the critical points by taking the derivative with respect to y, which gives us 6y minus 6 is 0, or y equals 1. Therefore, over this line segment, the given function f of xy may have an extremum at the point 4, 1. Next, we consider this side of the triangle, which is part of the line y equals x, where x runs from 0 to 4. Again, we restrict this function f over the line y equals x, which means we can replace y by x. And the resulting function is a function of the variable x. We solve for the critical point by taking the derivative with respect to x, which gives us 8x minus 10, and equating that to 0. Hence, x is equal to 5, 4. Therefore, the given function f may have an extremum at the point 5, 4, 5, 4, which is part of this line segment. Next, we collect all the critical points that we obtained from the previous steps. Recall that we have the point 2, 1, which is a critical point inside the region D, the points 2, 0, 4, 1, and 5, 4, 5, 4, which all appear on the boundary, and the point 0, 0, 4, 0, 4, 4, which are the vertices of the triangle or the intersection of the line segments that we have considered. Then, we compute for the value of f at each of these critical points. Now we see that the lowest value that f attains over these points is negative 7, and the highest value is positive 24. Therefore, we say that the absolute minimum value of f over the region D is negative 7 attained at the point 2, 1, and the absolute maximum value of f on the region D is positive 24 attained at the point 4, 4. This ends the first part of the lecture on absolute extrema of functions of more than one variable. I hope you learned something from this. Make sure to watch the second part of the lecture where we talk about a method of finding the absolute extrema of a function given a constraint. I'll see you on the next video.